Hi, my name is Danielle Tanzi, and this is my Physics 1 lab report. The purpose of this lab was to look into the principles of physics, namely Newton's second law, where force equals mass times acceleration, and understand the simple vertical motion of an object. In this experiment, both the observed and predicted motions of the object were derived by looking at both the change in position over time intervals and calculating the predicted position over the same time intervals. In both the observed and predicted values, the force appeared to be zero since the velocity remained constant and the object moved over a certain direction. As you can see here, this is a picture of the video that was evaluated. There is an axis in the purple lines, and 0, 0 is set at the center of the object, which will be moved over certain time intervals. The length of the object moved in 4 seconds and was calibrated, and its length was calibrated using the blue calibration stick, which measured 113 centimeters. The system here is a small magnet, and its surroundings are the board that it is sliding against. Using the mass tracker tool, the center position of the object was visually tracked over the time intervals of 1/30 seconds for a period of 0 to 4 seconds. The original time is 0 seconds, and the initial velocity is 2.6 meters per second. The mass of the object was sent to about 1 kilogram in both measurements, since it was unknown. Since the net force is 0, the effect of the mass on velocity change is irrelevant anyways. And as you can see here, the velocity is equal to the net force over mass plus the initial velocity. The tracker movements generated a table over several time intervals and also showed a graph showing how the position changed over a certain time period. Next, the code was used to give the calculated values and predicted values. Here you can see that the vector position is set to 0, 0, which is the center of the object, the same as the observed values, and the initial velocity is 0.262, which is the constant velocity shown in the first observed values. And the delta t is equal to 1/30, and the time as well is equal to 0. In the second part of the code, you can see the updated velocity and the updated position. Since the f net is set to 0, the velocity is constant throughout the whole interval. And the ball's position is equal to the velocity times that time period. Next, you can see a similar result to the observed velocities in a graph and a table as well. Next, the observed positions of time and the calculated ones are shown in the graph. The orange in both represents the calculated values, and as you can see, the r squared is completely linear, showing a completely force of 0 and a constant velocity. This makes sense because force is equal to mass times acceleration, and if velocity is constant, then the acceleration will be equal to 0. The one on the left represents the movement of the object as it was moving to the right. The one on the left is the same magnitude as the other one, except its direction is changed, showing that it would be multiplied by a different unit vector. Next, we're going to discuss some potential sources of error. It was hard to determine the initial velocity, so what I did was I took the derivative of the line of best fit, where the velocity appeared constant throughout. This may not be accurate and might not show the exact initial velocity that the object was moving at. The observed positions where 1/30 time intervals were a bit inconsistent, and this can be seen through the slight curve in the r squared graph. If the velocity is completely constant, the graph should be completely linear, showing that there is absolutely no net force. And additionally, the values seem to increase and decrease, which isn't really consistent and kind of shows human error in that, especially with inconsistencies in the y-axis since there appears to be no net force acting on the y-axis, and these y-axis changes are not consistent and overall average to around 0, indicating that this was also likely a human error.